Now, in this module, we will learn more about representation, that is how to find representation of number of molecules. I will discuss the representation of C2H point group, and I will use the unit vectors lying along XYZ axis, and these unit vectors, they will lie at the center. Then we will see, after getting the representation, we will verify the result, that the truthness, whether these matrices which we have generated are correct or not. We will also look in this module the representation of C3V point group, and also here again we will use XYZ axis, vectors along XYZ axis. Know about reducible representation, that is the representation which we have obtained in earlier modules. Are they reducible? So, we will learn what we mean by the reducible. Need for a simple method for finding reducible representation. 3n vectors as basis for representation of C2V point group. That is, we will take up XYZ axis or vectors on each and every atom of a molecule which belongs to C2V point group. Then we will find reducible representation directly by knowing that how many atoms are shifted and how many atoms are not shifted by any of these symmetry operations. And we will then get chi r, that is the character for symmetry operation R. Character here I mean to say that some of the diagonal elements of a representation. That is, we will find reducible representation, then take the diagonal sums of these matrices which will give us the character for R operation. Now, in earlier modules on representation, we have seen various bases used for generating the matrices for various symmetry operations, proper axis of rotation, sigma, center of inversion, etc. In this module, I will just see the representation for symmetry operations of C2H point group and C3V point group. And further, after getting these matrices, you will know that these matrices or matrix representation which we have obtained is a true representation, and we will compare then the group multiplication table, one due to the matrices, another due to the symmetry operation, and you will find that these are homomorphic with each other. There are infinite number of ways in which representation can be obtained by taking infinite different basis functions attached to the object in question. The number of functions attached to the object is called the dimension of the representation. We have seen the unit vectors lying along Cartesian coordinates as the basis for representations. These representations are again shown in table for C2V point group. Here, that is matrix representation of C2V point group using unit vectors. Now, what happens if I take E matrix and sum the diagonal elements, and the sum comes out to be 3. Sum of the diagonal element is known as the trace of the matrix. So, for E we get 3, for C2 we get -1, for sigma xz again we get 1, sigma yz we get 1. So, traces for this are 3, -1, 1 and 1. So, after getting the representation, we will take their trace or the character, and this will be now, if we take the trace sum of the diagonal elements from top left to bottom right of each of these matrices, we get the character of each matrix, which is written as unit vector in the above table. The representation is called tau reducible. It is desirable only to know the character of these matrices in the representation instead of writing full matrix for each and every operation. Now, for getting this into the module, I will just take the example of C2H point group. And in the C2H point group, I will take the example of a molecule dibromoethylene. Now, in dibromoethylene, the molecular structure of the dibromoethylene is like this, that is red balls, they represent dibromo, and this molecules lies in this plane. This is the plane of the molecule, that is all 4 hydrogens, 2 hydrogens and 2 bromines, they lie in this plane. And now I will put the 3 vectors like this or at the midpoint of this bond, that is at the midpoint of CC double bond like this. Now, for taking the CH2 point group, I will take the example of the molecule dibromoethylene, and dibromoethylene is placed like this into the plane like this. All the 4 atoms, bromines, 2 bromines and 2 hydrogens, they lie in this plane. And I take now 3 Cartesian coordinates or 3 vectors at the midpoint of CC bond. Here this CC bond, one of the bond is pi bond, which is perpendicular to the plane. And in this molecule, I will see the effect of C2 operation, sigma H operation, I operation and E on these 3 vectors. And one by one we will look now how they change when I go for C2 operations. Now I will concentrate on these x, y, z vectors along x, y axis for further mathematics for this point group. Now let us see the effect of E operation. E operation, let us see the effect of E operation on these vectors. What happens if I perform E operation on this? E operation means I am not doing anything to the molecule. It means this vector, this vector, this vector, they do not change. If they do not change, I will get a matrix which is 1 0 0 0 1 0 0 0 1. That is, it is shown into this over here. That is, none of the coordinates changes. So, for this E operation, I have 1 0 0 0 1 0 0 0 1 matrix. Now, let us see what happens when I carry out C2 operation. Here C2 operation I will carry out along z axis, that is this axis, and if I perform this C2 axis like this, what happens? Z axis, z vectors remain same, y axis changes sign, x axis changes sign, and so the matrix corresponding to this is minus 1 0 0 0 minus 1 0 0 0 1. So, this gives me a matrix which is for C2 operation on dibromoethylene. I am concentrating only these vectors which lie at the midpoint of the CC double bond. Now, let us go for what happens sigma, what happens center of inversion to these vectors. If I perform center of inversion, that is, I have to reflect through these points. This is will be, earlier it was like this. I have to reflect this through this and this through this and this through this. So, it will be now my it will be like this. That is, we will have like this. We will have our figures like this. Z axis has also gone to the negative side. This is x axis, this is y axis. So, all the axes, all the vectors have gone to the negative side, and so the matrix corresponding to this is -1, 0, 0, 0, -1, 0, 0, 0, -1. So, when I carry out operation I on these vectors, all the vectors change their sign and we get the given matrices. Now, let us see what happens if I go for sigma h. This is my sigma h which I am taking over here, and what happens? This vector and this vector, it remains into the plane, and this vector that goes down, that is, it goes below in this. Our figure will be just, we can concentrate, it can be like this. That is, only the z axis changes sign and no other axis, all other two axes, x and y axis, remain same. So, what will be the matrix now for? It will be 1, 0, 0, 0, 1, 0, 0, 0, -1. So, by performing this, we have a group multiplication table for C2H point group, which is given as over here. That is, first column gives the point group and the Tom matrix. For E, the matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. For C2, it is -1, 0, 0, 0, -1, 0, 0, 0, 1. For sigma h, it is 1, 0, 0, 0, 1, 0, 0, 0, -1. And for I, -1, 0, 0, 0, -1, 0, 0, 0, -1. Let us now construct group multiplication table of C2H point group using corresponding matrix for symmetry operations. Group multiplication table for C2H in terms of product of symmetry operation is given, which gives the various entries under E, C2, sigma, H and I. Now, let us go for the corresponding iteration. Let us now take various symmetry operation and product and verify our result. Now, first I will take I into C2 or C2 into I. What will be the net result? If I take C2 into I and look the group multiplication table, the result is sigma H. Now, let us do this in terms of matrices. I take the matrices corresponding to C2 and matrix corresponding to I, and then multiply them together. I get a matrix 1, 0, 0, 0, 1, 0, 0, 0, -1. What is this matrix? It is a matrix for sigma H, and also our symmetry operation product shows the result that C2 into I is sigma H. Now, let us take the another product C2 into C2 inverse. The result is E. Now, since C2 inverse is C2 only, we have the result as I take the matrix corresponding to C2, multiply with matrix corresponding to C2, and I get a matrix which is 1, 0, 0, 0, 1, 0, 0, 0, 1. What is this matrix? This is a matrix for corresponding to E. Now, let us take the third product I into I and see what is the result. Our symmetry product says I into I is E. Now, let us verify this result by taking the matrix multiplication. Matrix corresponding to I -1, 0, 0, 0, -1, 0, 0, 0, -1. Multiply with matrix corresponding to I -1, 0, 0, 0, -1, 0, 0, 0, -1. On multiplication, what we get? We get 1, 0, 0, 0, 1, 0, 0, 0, 1. What is this matrix? This is a matrix for E. So, we get the matrix for E. It means I is the inverse itself. Like this, every possible symmetry operation product can be worked out. These symmetry operation products in terms of matrices are then written in C2H group multiplication table, and these are shown in the table 3 over here, that is under E I have the matrices corresponding to E, C2, sigma H and I. Under the column heading C2, I have the matrix corresponding to E, C2, sigma H and I. Like this, all 16 entries have been worked out, and these are the representations for E, C2, sigma H and I. Now, similarly, you can work out the molecule which belongs to C3b point group, that is, you can take ammonia E, which has operation E, C31, C32, sigma V dash, sigma V double dash and sigma V triple dash. And for this we can take the example of ammonia molecule, and you can work out the representation similarly as we have done in the case of C2H point group. Now, in C2H point group, we have seen that when we perform symmetry operation, the x-axis goes into minus x-axis, y goes to minus y-axis. None is mixed with other. But in ammonia molecule, when we perform operation, we will not directly get x goes to x dash, y goes to y dash, but here these are mixed, and we will get different representation in which x and y z axis they mix with each other. We have seen earlier modules that what are the representation for such molecular point group. Now, in this module we have learned, that is, more about representation. More about representation means how we can generate representation by taking the examples of various molecules. And in this, I have taken the example of C2H point group, and I have shown you what are the symmetry operation of C2H point group, that is dibromoethylene. It has C2 axis, it has sigma H, it has I and it is E. So, the molecule belongs to C2H point group, and we have learnt how the XYZ vectors change when I perform C2 operation, I operation, sigma H operations, and these changes, that is change in direction etc., are represented as +1 or -1. If there is no change in direction, it is +1 effect. If there is a change in direction, it is -1 effect. And by making use of these plus minus, we have generated 3:3 matrices for each of the symmetry operations. In brief, regarding representation of C3b point group has also been mentioned, that is, the C3b point group, for example, ammonia molecule has E, C31, C32, sigma V dash, sigma V double dash, sigma V triple dash symmetry operations, and we can have here all representation. One point is there, that in this case x, y and z vectors, they mix with each other when symmetry operations are carried out. Now, so what we have seen over here, I have explained the meaning of reducible representation. That is, I represent by tau reducible if I take the diagonal trace of each and matrix and write down the numerical value. What is the need for representation has been explained. As I had told you, if I take benzene molecule with, then I have to deal with 36 into 36 dimensional matrices. So, this type of procedure is time consuming and too cumbersome in nature. So, there was a direct need for a representation. 3n vectors as basis for representation of C2B point group has been explained in this module with to a greater detail, and direct method for finding reducible representation has been explained just by taking 3n Cartesian coordinates. Now, to get some sight into how to get this representation, we take a water molecule, and on water molecule I will just take 3 Cartesian coordinates on each and every atom. This is my water molecule. I have numbered hydrogen also as 1 and 2, and this is my oxygen atom. In this molecule, I put 3 unit vectors on each and every atom. These are the 3 on this, 3 on this, and 3 on this. That is, there are 9 vectors now. They like this, then this, then this. So, I am having, instead of 3 vectors, as we have seen in earlier modules, dibromoethylene, we put down 3 Cartesian coordinates at the midpoint. Here each and every atoms has 3 Cartesian coordinates. So, I have to now look the effect of operations belonging to the C2B point group. What are the operations belonging to C2B point group? It is E, C2, sigma xz and sigma yz. Now, if I perform E, how many vectors are not shifted? 3 on each atom. 3 on oxygen, 3 on hydrogen 1 and 3 on hydrogen 2. So, 9 vectors are not shifted. So, what we will get? We will get a matrix representation of dimension 9:9, because I am now considering 9 vectors at a time. Now, similarly, if I perform C2 operation on water molecules, again 9 vectors will be affected. 3 on oxygen, 3 on hydrogen 1 and 3 on hydrogen 2. All 9 vectors will be affected. And here again I will get matrices corresponding to the C2 operation, which is of dimension 9:9. Similarly, you can carry out the sigma xz and sigma yz. You will get matrices corresponding to these operations, and the dimension of these matrices will be again 9:9. So, if I generate this 9:9 matrix and then I take the trace, that is the character of that matrix representation. In case of E over here, trace is 9, and in case of C2 over here, the trace is -1, and in case of sigma xz and sigma yz, trace is 1. So, after carrying out this C2 sigma xz and sigma yz operation on 9 vectors, I get 9:9 matrices representation, and I take a trace of that. I get 9 trace, then -1 trace and +1 trace. So, by carrying out such a process, this type of procedure is very cumbersome. Now, what happens? Suppose I take benzene molecule. How many atoms are there into the benzene? There are 6 carbon and 6 hydrogen. So, if I put 3 Cartesian coordinate vectors, 3 vectors along Cartesian coordinates on each and every atom, how many vectors I have? 36 vectors. So, if I perform symmetry or operation corresponding to the benzene molecule, I will get matrices of dimension what? 36 into 36. And if I take the trace, I will get the character for that symmetry operation into C6H6 molecule. So, just to deal with such a huge matrix, it is very time consuming and very troublesome procedure. So, is there any way by which we can get these traces or for reducible representation by simple method? Yes, we can do it provided we know something about the effect of symmetry operation on 3 Cartesian coordinates. So, there is a direct method for finding a reducible representation. By matrix multiplication rule, it is clear that if an atom or its associated vector is shifted in space by any symmetry operation, then the atom or its associated vector which are shifted will not contribute any to the character of the matrix, or there will be contribution 0 to the character chi r. In C2V point group, symmetry operation E does not shift any of the atom or its associated vector. C2 operation does not shift oxygen atom and its associated vector, while the vector of the two hydrogens are interchanged, that is, the hydrogen atoms are shifted. Sigma xz again shifts vector on two hydrogens and does not shift vector on oxygen atom. In case of sigma yz, all atoms and their associated vectors are not shifted. Only direction of some of the vectors are changed. Now, for 3n as the basis, it is generally true that the vector or atoms which are shifted during symmetry operation do not contribute or contribute 0 to the overall character of the matrix chi r. Only unshifted atom or unshifted vector contribute to the chi r. We will follow the procedure. Find the number of unshifted atom during a particular symmetry operation, one symmetry operation from each class. Then calculate chi r for every unshifted atom for every symmetry operation, taking one from each class. These contribution will be same for operation R in every point group when taken 3n vector as the basis. Tau 3n can be written in tabular form as shown in table. Now let us see how to get chi r for unshifted atom. For this, let us take 3n Cartesian coordinate vectors along the direction of x, y, z axis and perform all types of operation and see the effect. That is, I will just take, these are the 3 Cartesian coordinates, and I will just see the effect of various operations, not for any C2V point group, any other operation. Now, if I take E operation, this y, x and z x, they will not be shifted. And what will be the matrix? 1 0 0 0 1 0 0 0 1 and chi is equal to plus 3. That is, at the 3 diagonal elements, it is plus 3. Now, let us say the C2 operations. C2 operation I will carry out along this, that is like this. If I carry out like this, C2 operation, two vectors, they are now over here, they are shifted and two are not, one is not shifted as shown into the diagram. The result is minus 1 0 0, 0 minus 1 0, 0 0 1, that is chi is equal to minus 1. That is, if I carry out C2 operation on this 3 Cartesian coordinate vectors, I will get chi is equal to minus 1. What is the effect of I? I means I have to reflect through this one. This goes to down, this comes over here and this comes over here. That is, the result will be like this. Result will be like this. All the unit vectors along x, y, z axis have been changed and the result, the vector we are getting is minus 1 0 0, 0 minus 1, 0 0, 0 minus 1. What is the character now? It is minus 3. Effect of reflection operation sigma, that is, I have to see the effect of sigma yz. This is my sigma yz. this is my sigma xz and this is my sigma xy. Now what happens if I take sigma xy? This and this they remain same, this will go down. So only this will change, this and this will not change. What happens if I take sigma yz like this? If I take like this, z axis, this and y axis will not change, only x axis will go in this direction. What happens if I take xz axis? This z axis and x axis will not change, this will be go on this side. So just by seeing the effect of sigma on these, we generate matrices for these also, and these matrices which we get are this given as the result as -1 0 0 0 1 0 0 0 1 like this 1 0 0 0 -1 0 0 0 1, and the net result if I take the trace, it is comes out to be 1. Chi is 1 contributed by this. So I have seen the effect of your sigma xz, sigma yz, sigma xy. I have seen the effect of I operation also. Now what happens if I carry out Cn operation? Now here Cn operation, C2 I have seen. Now if I carry out theta rotation, it can be 120, it can be 60, it can be 72 degree rotation, then these x and y vectors, they will mix. They will not directly go into the minus and plus. They will mix together and we will get the representation as shown into the earlier modules, that is cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. That is the character for this is 2 cos theta plus 1. Character for Cn rotation is cos theta plus 1. Theta you can put down any value now. You can put down 90 degree, you can put down 45 degree, you can put down 120 degree, and by making use of this formula we can get the character for 3 unit vectors. Now what will be the effect of Sn operation? For Sn rotation, chi is given by 2 cos theta minus 1, because after carrying out Cn operation, I have to reflect this into a plane which is perpendicular to this. This is my Cn rotation and this is plane perpendicular to this. So in Sn I have to reflect through this plane, and in that case our z axis will also change the sign and the character now will goes to 2 cos theta minus 1. All these contributions can be summarized into table form. What is the use of this table? This table gives me the direct result. If I take 3n vectors along x, y, z vector as the basis, and if I take any molecule and if I know the unshifted atom and shifted atom, then I can find out reducible, tau reducible directly. So this table gives me the 3n Cartesian coordinates and their contribution chi. That is, for E it is plus 3, for I it is minus 3, for sigmas it is plus 1, for C2 minus 1. In general, for Cn rotation we have 2 cos theta plus 1 as the character, and for improper axis 2 cos theta minus 1 is the character. Now in next module we will look about, do we write down these representation as such? No, we will learn later on that we can make them still smaller. That is, by just taking the sum of the diagonal elements we can represent these effects. So this is the representation how we can carry out on a particular molecule just by taking the vectors along x, y, z axis. Even we can take the bond vectors as the basis for representation that we will learn in further modules. So, we have seen in this case that C2H point group, that is dibromoethylene, which has C2 sigma H I and E symmetry operations, we can generate 3:3 dimension representations.